So I will speak on a class of algebras, which I think is rather interesting and maybe important. But this, I call them Backström algebras. Now we will see why. The first mention about such algebras was in the paper of Ringel and Rogekamp of 1974. They consider a class of orders. They called it Backström orders. Since first they were considered in a PhD thesis of Backström, and they showed that the representations of these orders are almost the same as representations of a Kyiv. A class of Backström orders or Backström rings was considered by myself in 1990 in my paper about pure Noetherian algebras. Pure Noetherian means Noetherian, but with zero circles, so with no Artinian part. And I introduced that the class of rings, which now is called nodal rings. I didn't use this term there. And I showed that these are just the rings, Noetherian algebra, pure Noetherian algebra, such that the classifications of their finite modules is a tame problem. Further, Igor Bourbon and I consider the derived category of A modules. And then we use this term nodal rings. Okay. Further, Voloshin and I considered nodal curves. They are non-commutative curves, which are globalization of the nodal algebras. And finally, Vasil Zembek at about the same time considered finite dimensional algebras defined by the same conditions, so-called nodal algebras. By the way, nodal algebras include the so-called gentle algebras, skewed gentle algebras, and an interesting example is the algebra lambda n with this polynomial ring modulo or the square of maximal idea. Yeah, and that's all. Okay, what are Backström algebras? Backström ring A is such that A is contained in a hereditary left hereditary, contains its radical, which coincides with the radical of A, and I suppose that A and H are semi-perfect. So idempotence can be lifted modulo radical. Yeah, this is the definition of a Backström ring. If it is an algebra, then okay, then that is Backström algebra. And the Backström ring is nodal if, moreover, the length of tensor product of H with a simple H module, a module, is at most 2. Okay. Why do I think that this class of algebras is of interest? First of all, these algebras have a good categorical resolution. In some sense, they behave well with respect to homological algebra and so on. Namely, consider this so-called Auslander envelope. What is this? I consider the conductor of H in A, the annihilator of quotient H mod A. It is the same if we consider this as right modulus, left modulus, it is symmetric. And then I consider the ring of 2 by 2 matrices of the following form. Here we have A, H, C, H. This is Auslander envelope. It has very good properties. First of all, global dimension of A tilde is finite, and even it's at most 2. And it equals 2 if A is itself non-hereditary. Yeah. Then A tilde and A are related by so-called recurrent. Namely, consider the A tilde module, namely the first column, this one. Of course, it's endomorphism ring. Is isomorphic to A opposite. So we can consider the following functors hom over A tilde from P somewhere, or the same, which is important, that is the same as tensor product of P check over A tilde, where P check is the dual right module, the first row. Since it is both hom and tensor product, it has both left and right adjoint, left adjoint F tilde, F star, which is tensor product with P over A, and right adjoint F model, which is hom over A of P check somewhere. Then we have the following the following diagram of functors. We have A tilde modules. We have this functor F to A modules. We have both left and right adjoint. And moreover, the maps of identity functor to products and to identity, both are isomorphisms. Then we also have the kernel. It's embedding, which also has right and left adjoint. So this is the recurrent diagram. Well, moreover, the kernel of F can be easily described. It is isomorphic to the H bar modulus. H bar is H mod C. Okay. The most important is that we can do the same for derived categories. We can have derived category of A modules, A bar, A tilde modules, derived category of A modules. So since the functor F is, of course, exact, it has both left and right joints with data access, so we can just apply it to complexes component-wise. Then we have the functor from dA tilde to dA, and we have left hand joint, which is left derived of F star, and right joint, which is right derived of F. And certainly we have the same with the kernel. I will do it. One important note that though we have this, it is not the same for derived. It is not, as usual, it is not the same as derived category of H bar modules, usually. Well, and again, we have the same properties that identity functor is isomorphic to the F star and is isomorphic to the F RF. So since the A tilde is homologically good, it's finite global dimension, so we can consider this as a categorical resolution of the derived category of A. And this. Well, so we can say that the categorical resolution, the derived category of A behaves not worse than the derived category of A tilde. Okay, but there is another requirement for A tilde. Namely, if we take the second column, this one. So consider the module HH. Its endomorphism ring is the opposite to H. So we have the same, we can consider G from A tilde Q somewhere, and we have the same. Oh, I will write the diagram for derived categories, which is more important for me. We have here DG, LG star, RG, kernel, DG, the same. And in this case, kernel DG is very well behaved. Namely, kernel DG is isomorphic to the derived category, equivalent to the derived category of A bar, where A bar is A mod C, or better, it is A tilde more modulo the following. It's very important that this kernel, it is A tilde projective at that it gives us this. Why is it important? It is important that each recallment gives a semi-orthogonal decomposition. Of dA tilde. Namely, in our case, we have even two semi-orthogonal decomposition. It is the kernel of dg with the image of LG bar and also the image of RF bar and the kernel of dg. Note that these things are equivalent but not coincide. These are two different embeddings of dH into dA tilde. Why is it good? Now I consider the first one. Now we see that the first one, what is it? Semi-orthogonal decomposition. Semi-orthogonal decomposition means that there are no homomorphisms from right to left, and any object here is a cone of a map where A is here and B is here. Why is it important? We know that kernel dg is, what is this? This is a dA bar, and A bar is semi-simple. So it is the easiest possible category. This is its objects are just simple A tilde module, maybe lifted, shifted to the right and to the left as in any triangular category. What is the image of LG? It is, of course, d of H bar, and H bar is hereditary. Sorry, not bar. And H is hereditary. Since it is hereditary, then objects of dH up to direct sums are just shifted H modules. It immediately gives the following thing. We can calculate the Rouquier dimension. I recall that the Rouquier dimension measures the following thing. It is n if we can take finite set of objects such that iterating their direct sums and cones, we can in n+1 step obtain all objects of the right categories. In our case, in both the Rouquier dimension of semi-simple is 0. The Rouquier dimension of hereditary is 1, which implies that Rouquier dimension of d of A tilde is at most 2. And since we have this recallment, and we have these things, we have the same bound for A, the Rouquier dimension dA is also at most 2. For instance, this is so-called nodal orders for Backström orders for gentle and skewed gentle algebra for this strange algebra. It was very interesting for me that the Rukia dimension of its tribe category is 2. Yeah. Moreover, a remark. Suppose that our hereditary algebra H is of Dynkin type. So it is the algebra of the quiver of type A or something, the ADE. For instance, it is so for this algebra because in our case H is the following. It's a union of very simple Kronecker quivers. Yeah. Then Rukia dimension, since hereditary algebra of Dynkin type has finitely many indecomposable modules, and then the Rukia dimension of the H is also 0. And then the Rukia dimension of the A is at most 1. Which is very interesting for me. Yeah, but this is so, for instance, for gentle and skewed gentle. Because for them, the quiver is the union of several graphs of type A. Well, another thing which we can obtain from this semi-orthogonal decomposition is the following. Since it is a semi-orthogonal decomposition, we know that all objects of the A are isomorphic to the cones of maps where this is from the A bar, this is from the H. Yeah. Moreover, since one can easily see that that we only need to calculate the hom and x1. I recall that both things are just shifted modules, and we have to only to calculate homs and x1s. And one can do it. Yeah. We must calculate hom A tilde. And actually, every A bar model is direct sum of A bar. So we just calculate this one. And here we take any H model. And if M is H model, we must consider the corresponding A tilde model. I will denote it by M plus. And that is easy to calculate. What is it? It is just the annihilator in M of C. So this is the elements of M such that CU is 0. And X1 is, we must take hom A bar, take homomorphisms from C to N, modulo what we can say in a homomorphism. namely the homomorphism induced by the elements. Actually, we must, every element from here defines a homomorphism from C to M, which maps C to CU. So when we have this thing, so we obtain the so-called bimodal category. We have this bimodal H XY, which is our home XY. X is from dA bar, Y is from dH, but plus. Yeah. And the objects from dA bar are just the same as the elements of this bimodal. Okay. So it gives a very good approach to the study of the derived category of any Backström ring. But I think that my time is over, so I must stop. Thank you very much.